on topic 4 now, page 11, and this topic is titled Solving Linear Inequalities. So what we're going to do is start off by looking at the definition of a linear inequality. We're going to look at the procedure for solving a linear inequality, and then we're going to apply that procedure to solve two equations. In addition, we're going to look at some of the terminology that we're going to use, the mathematical symbols to represent different operations that we're going to do. So first of all, let's start off by looking at a definition of a linear inequality right here. And so we go back, and in topic 2, we know that a linear equation is defined as in the form ax plus b equals 0, where a and b are numbers that appear on the real number line, and a cannot equal 0. So we've got the same kind of thing over here, except that we're saying that in this case, instead of the equal sign, we're going to use a symbol that represents either greater than or less than. So the equation, instead of being ax plus b equals 0, is ax plus b is greater than 0, and ax plus b could be less than 0. In addition, one little extra point is that we can include the equal sign, and by this little line that appears, this is the greater than symbol. If we put a line underneath it, it means greater than or equal to. This symbol means less than is less than, and if we put a little straight line underneath that, we get is less than or equal to. So let's just go and look at some numbers. Here we have an example where 3 is greater than 2, so we've got the real number line, and this represents 0. These numbers are not to scale, so don't worry about it. 3 is a larger number than 2, so we write 3 is greater than 2. On the other hand, if we look at the relationship between minus 6 and minus 5, here all are negative numbers. This is 0. The positive numbers are over here. So then minus 6 is less than minus 5. This means greater than, this means less than. So the linear inequalities that we're going to deal with, some examples would be 2x plus 6 greater than 0. Here, a would be 2. A is the coefficient, or the number in front of the x. And b is this number, including its sign here, is plus 6. So what we're doing is trying to find the values of x that make 2x plus 6 greater than 0. Previously, what we've done with an equality is find the values of, let's say in this case, that make 2x plus 6 equal to 0. So here we want to, in a linear inequality, for this specific example, we're trying to find the value of x that make 2x plus 6 greater than 0. Another example would be of an ax plus b case would be and the inequality is 3x minus 7 is less than or equal to 0. Here, a is 3. A is always the coefficient of the number in front of the x. B is minus 7. So what we're asking is, what are the values of x that make this inequality true? If 4x is less than 0, here a is 4 and b equals 0. It's just a that cannot equal 0. B can equal 0. So here A. So what we're asking are, what are the values of x that make 4x times x less than 0? When we write x is equal to 8, there's only one value of x, one unique value of x, that is 8. The term x greater than 8 means that there are an infinite number of real number values of x which are greater than 8, but which do not include 8 itself. So we're not including 8, but any number that's greater than 8. That could be 8.00001, for example. So I could go 8.002. That would be another. I can keep on thinking an infinite number, meaning it's endless, that would fit the relationship of a value greater than 8. The term x greater than or equal to 8 means that x can equal to 8 or it can be greater than 8. So this completes just our basic definition of what a linear inequality is. Just to review here, this sign is greater than, this is greater than or equal to, this is less than, and this is less than or equal to. So how do we go about finding those values of x that fit a specific inequality? First thing that we have to do is isolate the variable x by operating the same on each side of the inequality and reversing the inequality when multiplying or dividing by a negative number. So we're going to explain what exactly we mean by that. Let's start off and say that we know 4 is greater than 3. 4 is greater than 3. So here we have 4. 4 is a greater number than 3. What happens when we multiply both sides of this inequality by negative 2? Now this is specific for negative numbers, what we're going to do when we multiply or divide by a negative number. So when we multiply 4 times negative 2, and then also do the same, multiply the right side by negative 2. So we start off with 4 greater than 3. We multiply the 4 by the minus 2 and the 3 by the minus 2. What we find is the result, minus 8, in relationship to minus 6, is no longer greater than, but less than. Minus 8 is less than minus 6. 4 times minus 2 is minus 8. 3 times minus 2 is minus 6. So the direction of the inequality has been reversed. The greater than sign becomes a less than sign. When we multiply an inequality by a negative number, we reverse the sign of the inequality. If we, for example, have 4 greater than 3 and we multiply both sides by 2 plus 2, there's no change. 8 would still be greater than 6. So let's review this again. 4 is greater than 3. We multiply both sides by minus 2, and the direction of the inequality reverses. Notice the direction of this greater than becomes less than. And that only happens with a negative number. On the bottom of the first page, you will see terminology. This symbol sort of looks like a sideways 8 is read as infinity, and the minus in front of it is read as negative infinity. So if we have a real number line where this is 0, plus infinity is shown with this arrow here, some number, undefinable number, infinity, on the positive side, and the negative side here with a negative in front of it, it represents negative. So we need these rules to solve linear inequalities. And we're going to look at the first problem here on page 11. 2x plus 6 is greater than 0. Now, what we're trying to do here, remember, is to find the values of the inequality, values of x, that make this inequality true. What values of x will make 2x plus 6 greater than 0, not equal to, greater than 0. So the first thing that we do to go from this line to this line is subtract 6 from both sides. So we're going to subtract 6 from the left, and we're going to subtract 6 from the right. But when we do subtract 6 from here, the 6's become plus 6 and minus 6 becomes 0, and this becomes minus 6. Now we want x by itself, not 2x, so we're going to divide the left by 2, and we're going to divide the right by 2, and we get minus 3. So the solution says that to this equation, any number greater than number 3, then the number 3 will give us the solution. So if x is greater than minus 3, that will be a solution to this inequality. Now, we can represent a solution in two ways. We can represent it with a solution graph, which is shown here. This is the solution graph, the top one. Or we can represent it with what we call a solution set. These two are equivalent. They're just two different ways of representing. So over here, we draw a number line, put the 0 in here, and show minus 3. And we make this line bold in this direction, meaning it keeps on going. We have this heavy arrow here. This is bolder. This is weaker over here. This is minus 4 and minus 5, etc. keeps on going. But we want a number greater than minus 3. So we start at minus 3 and we make this number bold over in this direction to show any number greater than a minus 3 would be a solution. So that's the graphical way. Now, because another way of representing this is to write that we're going from minus 3, and it can be any number bigger than minus 3. So, and it keeps, this would be any number on this line that keeps on going. We show the infinity. So, any number between minus 3 and plus infinity would be a solution set. Now, because we're not including the minus 3, there's no equal sign here. We put a rounded bracket. We'll see what happens when a number is included. The infinity, because it's undefined, is shown also with a rounded bracket. Either of these, this or this, represent satisfactory representation of this. Now, note that for the graph, the line is bold between minus 3 and infinity. Right here, it's bold. The solution set is an alternate, non-graphical way of expressing the solution. The rounded bracket associated with a minus 3 indicates that the solution x greater than minus 3 and x is greater than minus 3 and does not include the minus 3. If the solution set were x greater than or equal to minus 3, this would be shown with a square bracket. So there's only two ways to show this. If the minus 3 was included, put a square bracket like that. This part would be exactly the same. There is a rounded bracket associated with infinity. infinity because it is undefinable. So over here we put a rounded bracket. Now we have ways of checking the answer. They're not foolproof, but they can help. One can check the answer to the inequality by using a number that falls within the interval that holds the inequality true, and use a second number that holds the inequality false. For example, we could use a number greater than -3. We frequently use 0 because 0 is easy to operate with in terms of multiplication, addition, etc. And so we often use the number 0. And if you look at the solution set here, you can see 0 lies within the answer of the solution set. So we should just choose 0. We don't have to, but usually it makes it easier. So we want to see if we replace the x with the 0 in the inequality, does that make that inequality true? So we're asking, is 2 times 0 plus 6 greater than 0? In other words, it's 6 greater than 0 because 2 times 0 is 0. We have 6 is greater than 0. The answer is yes. So we know that we've randomly chosen 0 as a number that applies within the solution set right here. And it works out that when we put it into the inequality, it works. Now, we could choose, we know that the number -4 is over here. And the number -4 is less than -3. It's not greater than -3, so we can choose -4 because it lies right here. It's not in the solution set. The solution set is from here to here. We're going to go and try that out. We know that -4 does not lie within the solution. So we, instead of x now, we replace it with -4. 2 times -4 is -8 plus 6. And we still have the greater than 0. Is -2 greater than 0? No. Therefore, -4 should not be part of the solution set. So to review what we've done here, we found the solution set was a number greater than -3. To check the answer, we chose a number that lay within the solution set, 0. We can see that it does. And we chose a number that was outside of the solution set. So with the number in the solution set, we put it back into the original equation, and the original equation still held true. When we put a number that did not lie in the solution set, in this case -4, into this equation, this statement was no longer true. So these are ways that we can check. In other words, we check with a number that lies within the solution, and we check with a number that lies outside of the solution set. Okay, let's go to the second example here. And we're asked for what are the values of x that make this inequality true? So we do the same kinds of things that we did with regular equations. We want the variable on the left and the number on the right. So the first thing I'm going to do is get rid of this 8 by subtracting 8 from the left and subtracting 8 from the right. So I subtract 8 from each side, and if I subtract 8 from this, the 8, we get rid of this 8. And if I subtract 8 from 2, 2 minus 8 gives me -6. So I'm left with -3x greater than or equal to -2. I want x alone. I want to find x by itself. So I have to divide this side by -3. When I have to divide by multiply or divide by a negative number, the direction of the inequality changes. -3 divided by -3 here gives me +x. -6 divided by -3 gives me plus 2, but the direction of the inequality changes. This says that any number that's less than or equal to 2 will be a solution, but it must include the number 2. So here you see the number 2, and we bold the line over here, okay, going in the direction, because the number can be any number less than 2 that appears on the number line. And so obviously on this side of 0, the numbers are negative. We have a minus infinity. Minus infinity is undefinable. So we have this rounded bracket within the solution set. And this is square because it can equal 2. So as we said before, there are 2 ways to represent the solution graph and the solution set. You can use the square bracket right here to represent the 2 and the minus infinity here. So note that for the solution graph, the line is bold between minus infinity and 2 right here. This is minus going in the direction of minus infinity and 2. It's bold. We make it darker. The solution set is a non-graphical alternative way of expressing the solution. The square bracket associated with 2 indicates that the solution is less than or equal to 2. So when we've got an equal sign, we put this square bracket in there. If the 2 was not included, we would have a rounded bracket right here. The infinity, as I've said, is undefinable, so we have a rounded bracket. So what we're going to do is, again, check this problem, and we're going to check with a number that we know lies within the solution set. Again, we're going to use 0 because it's easy to use. So we'll start with 0, and we'll plug it into 8 minus 3x greater than or equal to 2. So instead of the x, we put the 0. 8 minus 3 times 0 greater than or equal to 2, question mark. So really, the 3 times the 0 gives us 0 is 8 greater than or equal to 2. Yes, so 0 lies in the solution set. We're going to choose a number now that does not lie within the solution set. I can see that the number 3 doesn't lie in the solution set. I don't have to choose 3, but I can see it's easy, because I see very clearly that it doesn't lie in the solution set. So I ask myself, 8 minus 3 times x, x is 3, is that greater than or equal to 2? So I get 8 minus 9, which is minus 1. Is minus 1 greater than or equal to 2? No, minus 1 is less than 2. Minus 1 is less than 2. So the answer is no. So the solution set does not include x equal to 3. Okay, now we will go on and we'll look at page 12. And this is just a review of what we just spoke about here. We just spoke about this, that if we have 3 greater than 2 and we multiply each side by minus 1, then the direction of the inequality reverses. So we got 3 greater than 2, minus 3 is less than minus 2, which is true. So 3 greater than 2, multiply the left by minus 1, multiply the right by minus 1, minus 3, and change the direction of the inequality. Now what we're going to do is look at 2 problems and see if we can solve them. We're going to show it in more detail. So here's problem 1. And again, we're looking for the values of x that make this inequality true. So you'll see that I have a denominator here where there's a 3. First thing, as we've seen in the number problems, is we want to get rid of the denominator. So then I have no fractions anymore. I'm going to multiply both sides by 3. And the 3 here cancels. This 3 cancels with this 3, and I'm left with 5x minus 2. And if I multiply this side by 3, I have to multiply this side by 3. So the sole purpose of multiplying the left by the 3 is to get rid of the 3 on the denominator here, because this 3 is on the numerator, this 3 is on the denominator, and so I have 3 times 2 here is 6x plus 1. I'm going to use the distributive rule. 6 times x gives me 6x, plus here 6 times 1 gives me 6. So now I have 5x minus 2, 6x plus 6. I want to get the variable on the left and the number on the right. So if I take 5x, if I take the 6x, bring it over to the left side, I'm left with minus x. If I take the minus 2 and bring it over to this side, it becomes plus 2. So I have 8. So all I'm doing is moving the numbers from the left to the right and the variable from the right to the left. I come up with minus x is less than or equal to 8. I want to multiply this by minus 1, which is a negative number. The direction of the inequality changes. And I have x greater than or equal to minus 8. I can represent this in 2 different ways. And you can see here, here's the minus 8. Here's the 0, so I count minus 1, 2, 3, 4, 5, 6, 7, 8. It includes the minus 8, the equal sign, so that's a square bracket. I bold this, and I keep the arrow here showing that it's going to infinity. And so because an infinity is undefined, I put it around the bracket. Because the equal sign is included with the minus 8, I include that in the solution set. Either of these two represent equivalent ways of representing the solution, either the solution graph or the solution set. Okay, so we can choose the check the answer by choosing numbers that fall within and without. So here we're going to actually do 3 different numbers. We're going to start off, and I'll explain why. You don't have to do this. We're going to start at the boundary where the x equals the minus 8, because we know one of the solutions is x minus 8. So we're going to put that in. And you have to go back to the original equation. So if you go back to the original equation, it's right here. There's the left side, and here's the right side. So I'm going to substitute x equal to minus 8 into the left side right here. So I've got 5 times minus 8 minus 2. 5 times minus 8 is minus 40. And I subtract 2 to get minus 42. I divide by 3 to get minus 14. The right side is 2x plus 1. And if I substitute the minus 8 plus 1, I get minus 14. So the left side equals the right side. Now, because that represents the equal situation in the equation. Now we could choose a number greater than minus 8. This still lies in the solution set, and the example would be 0. So we go back up here. You can see that 0 would still lie within the solution set, as does minus 8. So go back, choose a number greater than minus 8, 0. The left side is 5x minus 2 divided by 3. We put the 0 in, and what we get is minus 2/3. So 5 times 0 is 0, minus 2/3. The right side would be x equal to 0 is 2. So now we ask ourselves, is minus 2/3 less than or equal to 2? And the answer is yes. So the value 0 lies within the solution set. So both 8, minus 8, and 0 lie within the solution set. Now we're going to choose a number that doesn't lie in the solution set. How do we do that? We go back and we see right over here, this doesn't lie within the solution set. So we're going to choose minus 9. And choose minus 9. We substitute this into the left side of the equation. We get 5 times minus 9 for the x minus 2. This comes out 5 times minus 9 is minus 45. Subtract the 2. We get minus 47 over 3. And we divide 3 into 47. We get minus 15 and 2/3. 3 times minus 15, and then we add the 2 to that, we get minus 47. So this is minus 15 and minus 2/3. Now the right side, if we put minus 9 in, comes out to be minus 16, because minus 9 plus 1 is minus 8, that's minus 16. So we ask ourselves, the left side, is that less than or equal to minus 16? Is minus 15 and 2/3 less than? No, it's greater than. Minus 15 is on the positive side. It's not less than minus 16. It's greater than minus 16. Therefore, minus 9 does not lie within the solution set. So this gives us a idea of how to solve a problem. We're going to go and look at the next problem to solve, which is here. And what we're asking here is, what are the values of x that make this inequality true? What are the values of x that make this inequality true? So we want x by itself. So I don't want this minus 9 here. So I'm going to add 9 to this part right here. And if I add 9 to this, I'm going to add 9 to this, and I get 12. I got to add 9 to this to get 20. This way I just have 4x. So I'm adding 9 to this, I'm adding 9 to this, I'm adding 9 to that. So the inequality should still hold true. Now I'm going to divide. I don't want 4x, I want x. I'm going to divide this by 4. Well, if I divide that by 4, I have to divide the 12 by 4, which gives me 3. And I have to divide the 20 by 4, which gives me 5. So this says 3 is less than or equal to x, which is less than 5. So 3 is less than or equal to x, meaning it's lower than x, and x is lower than 5. So we can show this as, in a sense, as a range between 3 and 5. Really, this represents the range between 3 and 5, but it includes the number 3, so there's a square bracket there. So the solution set is 3 to 5. Because the 5 is not included, because there's no equal sign here, we put a rounded bracket. Because the 3 is included, we put a square bracket. So 3 is less than or equal to x is less than 5 can be read. 3 is less than or equal to x. In other words, x is greater than 3. What we're saying is x is greater than 3 if we say that 3 is less than or equal to x. We're saying x is greater than 3. And x is less than 5. So the solution lies between 3 and 5, but also includes the number 3. That's why we have the equal sign, because that it can include the number. We can, as you see, this notation here, if I put a 2 less than between a lower number and a higher number, that indicates that there's a range, so over which the interval is true. Of course, I can include equal sign here, and I can include an equal sign here. But if I wanted to show that a number lay between, let's say, 12 and 14, I put 12 here, and I put 14 here. If I wanted to include the number 12, I put an equal sign here. If I wanted to include the number 14, I put a little bar under there to show that it was also equal. So that gives us an idea of how we use interval